Good morning, everybody.
Good morning.
So in the previous class, we looked at the relationship between the h of z and h of n, and we looked at obtaining the h of e to j omega from h of z. So we're going to be continuing today, and our ultimate goal is to do the following. I want to be able to go from h of n to a difference equation and go from h of n to h of z and go from h of z to a difference equation. So the three representations that we are familiar with of a system are h of n, the impulse response, a difference equation, and h of z. So our goal is to be able to go from one to the other seamlessly. So, and of course, if we have h of z, then we also have h of e to j omega, which is the frequency response. So if I have h of n, how did we go to get h of z?
Z transform.
Z transform. So if I take Z transform, I can get h of z, and vice versa. If I have h of z, I take inverse Z transform, and I will get h of n. And if I have h of z, how do I get h of e to j omega? Just plug in z equal e to j omega. And then at the end of the class, in the previous class, we said, okay, then if I have h of z, and I can plot the poles and the zeros of h of z, I can, from the graph, be able to tell what kind of filter I have by looking at where the poles and zeros are. Make sense? So we've done an example, so just a refresh to one more example. So for instance, if I have h of z, z divided by z plus 1/2, then I can plot the pole and zero. This is the unit circle. And I have a pole at negative 1/2. I have a zero at the origin. And therefore, I can plot the frequency response of this filter, of this h of z. And we said we're going to go from negative pi to pi. And the way we're going to do it, we're going to walk around the unit circle because it represents e to j omega. E to j omega is the unit circle. And if I am at the unit circle, and if I start when omega is equal to 0, so this corresponds to omega equal to a 0, then what is h of z? I can evaluate it by taking the distance to the 0 divided by the distance to the pole. What's that going to equal to? 2 over 3. 1 over 1.5. 2 over 3. The distance to the 0 is 1 divided by 1.5. And then as I go around the unit circle, omega is increasing. Omega here is pi over 4, pi over 2, and so on, all the way to a pi, and all the way back to 0. And therefore, what's going to happen as I go around the unit circle? The distance to the 0 is not changed, because it's at the origin. What is changing? The distance to the pole. And what's happening to that distance? It's getting smaller, and therefore h of z is going to get bigger. Agree? So when I am at pi, I'm going to have a value that is going to equal to a 2, which is, if I'm here, the distance to the 0 is 1 divided by 1/2, which is going to equal to a 2. And therefore, if I look at this filter, what this filter looks like? A high-pass filter. Now, after we introduce the relationship between h of z and the difference equation, we'll go back to MATLAB and we'll run some simulation, and we'll show you indeed this is a high-pass filter.
How did you get 2/3?
The 2/3 is when omega is equal to a 0. It means I am at this point here. When I take the distance to the 0, it's a 1. The distance to the pole is 1.5. So it's 1 over 1.5. Make sense? Of course, this is distance to 0, which is at the origin, divided by distance to pole, which is going to equal to 1 divided by 1 plus 1.5. That's the same. This is the same as saying z equal e to j omega, but omega equal to a 0. Therefore, z is equal to a 1. Therefore, plug in h of z. I'm going to get 1 over 1 plus 1/2, which is 2/3. Does that make sense? These both are equivalent. This is determining it graphically. This is analytically plugging value. But if I were to use MATLAB, I'm going to use it this way. If I have a graph of the poles and zeros, I just want to get a rough idea of what this filter is doing. I can just look where the poles are, where the zeros are, and determine how it behaves. Does that make sense?
Yeah.
Everybody? Because this is very simplified, because I have only one pole, one zero. In general, I'm going to have multiple poles and multiple zeros, and therefore it's going to be more interesting than just a simple pole and zero. Okay. So what we're going to be doing today that is new is that we're going to look at the relationship between the z transform and the difference equation. So we're going to try to relate the difference equation to h of n and h of z, or to h of z. We're going to look at the relationship between z transform and difference equation. And of course, I want to emphasize, once you have all these relationships figured out, like this is really the core of the course. If I can go from h of n to a difference equation to h of z to h of omega, then you'll have a very good understanding of all these different representations. So how do we go between the z transform and the difference equation? We're going to be using the type shift property that says x of n minus n0 has a z transform that is z to negative n0 multiplied by x of z to go between a difference equation and transfer function. And this is valid for right-sided sequences. Which is what we're interested in. So if I have a difference equation and I want to go to the z transform to h of z, what do we have to do? The first step, we're going to take the z transform of the difference equation. We're going to keeping x of z and y of z, and using the time shift property. And the second step, we're going to factor out y of z and x of z. And the third step, we're going to express h of z as equal to y of z divided by x of z. So to go from a difference equation to h of z, we're going to use these steps. And a fourth step, which we might need, if needed, we can multiply by z to n multiply by z to n over z to n to get all positive power. Sounds good? We'll do an example in a minute, but let's look at how to go from a z, h of z to a difference equation.
So the difference equation, it's been a while. It's how we defined the filter in the past?
I mean, we briefly mentioned the difference equation as a representation of the system.
Okay.
But good question. I mean,
Is there coefficients or something?
the point we're trying to make is all these represent the same thing. H of z, h of n, h of h omega, difference equation. They all describe the same thing, and I can go between them.
What's the advantage of these? Of difference equation?
Good question. What is the advantage of a difference equation? You want me answer, or you want me let you answer after we do an example?
I'll figure it out.
Okay. So, but if we don't answer it by the end of the class,
I'll try to pay attention.
no. Try to see if you can, if your intuition helps you feel like, oh, okay, that's useful. Okay, so how do we go from h of z to a difference equation? We're going to express h of z, which is y of z over x of z, as equal to h of z. And we're going to cross multiply. We're going to take inverse z transform z to n0 multiplied by f of z is going to give me f of n plus n0. We're going to take, we're going to perform time shift and rearranged So we can get y of n equal the summation of ak y of n minus k plus the summation of bk multiplied by x of n minus k. Okay. Straightforward steps. Let's do an example, examples to demonstrate all these. So let's say we are given a difference equation that says y of n minus a 3 over 5 y of n minus 1 plus 2 over 25 y of n minus 2 equal to x of n minus 2x of n minus 1 minus x of n minus 2. Is this a filter? Is this an IRR or FIR? IRR. Why? Because if I move these to the other side, the output depends on the output and the input. Now, what is the advantage of this form? Can anybody think of advantage of this?
You can factor out the.
I'll give you 5 seconds.
You can take into account all the data?
What else? If I tell you here is a filter, can you go implement the filter? And you have a choice. I can give it to you as h of n, as h of z, h of e to j omega, or a difference equation. Which one would you choose?
Which one's easier in MATLAB?
Which one you think would be easier? I mean, apparently it has to be this because I'm trying to. I can go to MATLAB, put it in a loop. If I know the input, I can loop through all the values and calculate the output. Does that make sense? How else would I calculate the output of the filter? How would I implement this filter? With the difference equation. Does that make sense? If I know the input, if you tell me this is the noisy signal that I have, x of n, and I tell you, oh, this filter will take care of that noise, what do you have to do? Just going to create a loop in MATLAB, calculate y of n equals to 3 over 5 y for n minus 1, minus 2 over 25 y for n minus 2, plus x of n minus 2, x of n minus 1, minus x of n minus 2, and loop. Every time you calculate the output, store it so you can use it, and keep calculating, it will give you the output. Does that make sense?
Yeah.
Everybody? Okay. So if we are analyzing the filter, h of z is very useful because we can plot the poles, zeros, we can plot the frequency response. But if I'm implementing the filter, I'm going to use a difference equation to implement it. Now, how do I go from this difference equation to h of z? Using the steps that we just highlighted, we're going to take the z transform of both sides of this equation. What is the z transform of y of n?
Z?
Y of z. What is the z transform of y of n minus 1?
Y of Z to the negative 1?
Excellent. Z to negative 1 multiplied by y of z plus 2 over 25 z to negative 2 multiplied by y of z equal to x of z minus 2 z to negative 1 x of z minus z to negative 2 multiplied by x of z. Agree? Okay. What do we do next? I'm going to factor out y of z. So I'm going to take y of z as a common factor out. I'm going to get 1 minus 3 over 5 z to negative 1 plus 2 over 25 z to negative 2. And this is equal to x of z multiplied by 1 minus 2 z to negative 1 minus z to negative 2. Then I'm going to write y of z divided by x of z. This is equal to h of z. And this is going to equal to 1 minus 1 minus 2 z to negative 1 minus z to negative 2 divided by 1 minus 3 over 5 z to negative 1 plus 2 over 25 z to negative 2. Go ahead.
X can never be 0 because.
Yeah.
X can be 0 if there is no input or the input is 0.
Okay.
What is this y of z and x of z? This is my system. I have input x of z, output y of z, and a transfer function h of z. Together? Y of z equal h of z multiplied by x of z. If x of z is 0, y of z is 0. If there is no input here, there is no output here. Okay, what is the next step we're going to do? We're going to multiply the numerator and denominator by z squared. Why are we multiplying by z squared?
Get all positive powers.
Yes, to get all positive powers, because that's the convention we're using in this class, all positive powers. So we're going to get z squared minus 2z minus 1 divided by z squared minus 3 over 5 z plus 2 over 25. And this is my transfer function. Together? So we went from a difference equation to h of z. If I want h of n, what do I have to do? I take the inverse of h of z. Divide by z is part of taking the inverse. So taking inverse z transform will give me h of n. Does that make sense? So what is h of n that implements this difference equation? I can just take the inverse of h of z to get this h of n. Okay. Let's do another example where we are given h of z equal to z minus 1/2 divided by z squared plus 3 over 4 z plus 1 over 8. And we're going to find the difference equation. So y of z divided by x of z is given by z minus 1/2 divided by z squared plus 3 over 4 z plus 1 over 8. What do we do next? Cross multiply. And that will give me y of z multiplied by z squared plus 3 over 4 z plus 1 over 8 equal to x of z multiplied by z minus 1/2. What do we do next? We take the inverse z transform. What is the inverse z transform of y of z multiplied by z squared? Y of n plus 2. What is the inverse of y of z multiplied by z plus 3 over 4 y of n plus 1 plus 1 over 8 y of n. And this is going to equal to x of n plus 1 minus 1/2 x of n. Together? Everybody? What do we do next? We're going to shift, since the output n plus 2, we're going to shift it all by 2. And that will give me y of n equal to -3 over 4 y of n minus 1 minus 1 over 8 y of n minus 2 plus x of n minus 1 minus 1/2 x of n minus 2.
So you just take your highest order?
Yeah, highest y, highest index of y, and we want to make it y of n, because this is the convention of how the difference equation is this way. And this one will be confusing. Always when you look at the difference equation, you're looking for y of n. So if I write it y of n plus 2, you're not going to easily see what this y of n is. Okay. So with that, let's go back to the example that we've done at the beginning of the class. So we have h of z, that was z over z plus 1/2. What is the difference equation of? This is the filter that we started with today. So I can write y of z over x of z equal to z divided by z plus 1/2. And therefore, z y of z plus 1/2 y of z is equal to z multiplied by x of z, and y of n plus 1 plus 1/2 y of n equal x of n plus 1. I can shift by 1, y of n, bless you, minus 1/2 y of n minus 1 plus x of n. Agree? And we said, what kind of filter is that?
High pass.
High pass filter.
So
Go ahead.
to me, it's confusing that you already have a y of n.
Uh-huh.
Okay. So, oh, n plus 1 is higher. Okay, okay.
Yes, we can have y of n, we can have y of n here and x of n, if it is an IR filter. The output can depend on previous outputs and inputs. Okay. So if I have this filter, we say this filter is a high-pass filter. How do I show it is a high-pass filter? I'm going to come to this filter, and I'm going to apply two signals. What is a very low frequency signal? No. Impulse is not. Impulse is not.
Step response.
That's a constant. Omega equal to a 0. A constant signal.
Yeah.
So very low frequency, omega equal to a 0. I have a signal that looks like this. Good? What is a very high frequency? Remember, we said the highest frequency, pi. So if I take a cosine of a pi, what am I going to get? A signal that oscillates like this. Agree? This is 1, 1, 1, 1, 1, 1, negative 1, 1, negative 1, 1, negative 1. This is omega equal to a pi. This is low frequency. This is high frequency. Now, if I apply to this filter, what do I expect this filter to do?
Pass the high.
It's gonna like this one. It's gonna dislike this one. It's gonna attenuate this one. It's gonna amplify this one. And let's see what this filter is gonna do. Y of n is gonna equal to y of n, and let's say this is where we're starting at 0. This is at 0. What is the output of this filter when I apply just a constant signal? First output is going to equal to x of n at 0, which is going to equal to a 1. Agree? When n is 0, y of 0, I'm going to assume there's no initial condition. So I have x of 0, which is a 1. When n is 1, what is the output going to equal to? What is it? 1/2. When n is 2, what is the output going to equal to? What is it? A quarter. And it's going to get smaller and smaller. What did it do to this signal? Attenuated the signal. You see? Now let's see what happens to the other output, to the other input when we apply it. At 0, we're going to have a 1. At 1 is going to equal to minus 1/2 times this one minus a 1. What is it going to be? Minus a 1.5. Agree? You see it? Just plug in, like iterating. Y of 1 minus 1/2 multiplied by the 1 plus x of n, which is negative 1, so minus 1/2.
So it's actually being amplified.
It's being amplified. What is when n is equal to a 2? It's going to multiply this by 1/2, so 0.75, plus the input, which is a 1, it's going to become 1.75. You see it? Everybody? So this signal, the low frequency, got attenuated. The high frequency got amplified. And in this case, it's going to have a larger amplitude. Any question? Is that clear? Okay. So let's run this also in MATLAB. New MATLAB?
Still got 2021.
I think what is the one we have in on?
On the apps, it's 2021, but they're the same, right?
Probably very minor changes. Oh, this is 2022. Yeah, brand new. Okay. So we're gonna do DSP.
Just glad it's not Octave.
What is it?
Just glad it's not Octave. The free wannabe MATLAB.
Well, I use that a lot though at home. Okay.
You don't want to pay the $10,000 license.
Just environmentally friendly free version. Okay, so we have two signals, low frequency a high frequency. How do I know this is a low frequency?
So make it slow.
Because it is a 0.02 pi. So that's a low frequency. This one is 0.8 pi. The closer I am to a pi, the higher the frequency. The smaller the omega, the smaller the frequency. So I'm going to take them through our filter, and how I'm going to generate the output of the filter using my difference equation. Just going to do calculate the way we calculated it in a minute ago. And then I'm going to plot it, plot the output. Now, if you remember, we looked at a second h of z at the end of the class. It was z over z minus 1/2. Do you remember? What was the z minus z 1/2? Z plus 1/2, it was a high pass filter. What was the other one?
Low pass.
A low pass filter. So if I run this, I'm going to run it through both. And if we run it, it's supposed to auto hide. Okay, thank you. Okay, so if you look at the input, look at the output, and look at the third output. So if you look at this filter, the high frequency is attenuated, low frequency is amplified, low pass filter. If I look at this filter output, the other way around. The high frequency is amplified and the low frequency is attenuated. The low frequency is attenuated, the high frequency is amplified. You see it? How did I generate these results? Using the difference equation. I just looped, and again, just remind you that we have two filters, the one that we saw at the end of last class and the one we saw today. So to generate any output, just loop through and assume initial conditions and just loop through and calculate the output. Does that make sense, everybody? Now, this is not the easiest way to generate the output. MATLAB has a filter command that you can just generate an output by just passing the filter parameters. But for our purpose, for the time being, we're just going to use the difference equation to generate it. Okay. Let me just snip this. I don't know if anybody is using MATLAB. Probably should give you more assignments with MATLAB. But nevertheless, when you're studying and if you want to make changes to it and see how it works, here is the code. Okay. Any question? Okay, so the next thing we're going to look at is how to solve these difference equations. So what is one way of solving the difference equation? The one we just seen, which is iterate all over the values and get the output. But we're going to be able to solve it using Z transform. So if we are given an nth order difference equation with n initial conditions, so we have an equation, the summation from k equals 0 to n a sub k y of n minus k equal the summation from k equals 0 to m bk x of n minus k, and we have y of negative 1, y of negative 2, y of negative n minus 1. Okay, so I want to be able, our goal is I want to find the output due to a specific input. Is that clear? Makes sense? I mean, this is similar to differential equations. When you have a differential equation, you want to solve it for a given input. Okay. Our solution is going to give me y of n, y plus y. What are the two outputs that I'm going to have as a result of applying an input? Okay, I'll give you one of them, and you guys give me the other. We're going to get an output when the initial conditions are equal to 0. What is this output going to do to input? What is the second output going to be due to? Initial conditions. So the output, when we solve this difference equation, the output is going to come from the input that we're applying and from the initial conditions.
So was one of those supposed to be an X?
One of these.
It was like y of n plus y of n is equal to y of n.
So y of n, this is the output.
Okay.
The output is going to have two components. One output that's going to come from initial condition, from the input, from x, and one is going to come from initial conditions.
Yeah. Is that like the natural solution, general
Yes.
solution?
Yes, the forced response and the transient response. The natural response. Very good. So if we don't have initial conditions like we've done before, this component is going to be 0. There's no initial conditions. If there are initial conditions, these initial conditions are going to show up at the output. Is that clear, everybody? We're going to do an example, so we'll hopefully become more clear. So to do this, we're going to take the Z transform of the difference equation. And we're going to be using the time shift property. Now I know we mentioned this property, we never used it, so we're going to be using it to solve the difference, to find the output to a difference equation. What this property says, if you have x of n minus n0, then the z transform for it is going to be z to n0 multiplied by x of z plus the summation from m equal 1 to n0 x of negative m z to m. And this x is not the input, this is in general. Let me just make it a y so it's not confusing. Y of z, y of negative m, z to m. Together? This is the time shift property that we introduced probably a few classes ago. Looks confusing, but we'll clarify it. We'll see what it means. Second, we're going to convert to positive powers of z. And third, we're going to express the equation as y of z equal n1 of z divided by d of z multiplied by x of z plus n2 of z divided by d of z. Now this is going to give me the two components of the output. This is when the initial conditions are equal to a 0, and therefore this is going to equal to h of z multiplied by x of z, and this is due to initial conditions. So this is when x is equal to a 0. Together?
The denominator is the same, right?
Yeah. Remember, when we calculate h of z, what is h of z? Y of z over x of z when the initial conditions are 0. Make sense? Remember that? Transfer function. So if I set this initial conditions to 0, I go back to y of z equal to h of z multiplied by x of z. Okay. The fourth step, I'm going to substitute for x of z and take inverse z transform. Okay, let's see what all this means. Okay, who can remind me what is it we're trying to do? Solve for y of z. We have a difference equation. We are given an input. And let's see what the expression for the output is going to be. Make sense? So keep that in mind. Okay, so let's look at an example. If we are given the difference equation, that is y of n minus 5 over 4 y of n minus 1 plus 1 over 4 y of n minus 2 equal x of n minus 2 x of n minus 1. And I'm given initial conditions. How many initial conditions I'm going to have here? 2. So I'm given y of -1 is equal to 4, and y at -2 is equal to -4. And what else I need to determine y of n? I need to know what that input that you're applying. So we are given x of n equal to 1/2 to the power of n u of n. Why do I have initial conditions for y, but I don't have initial conditions for x?
This assumption
What else?
starts at 0.
Because I know x of n. X of n is known. You know what I'm saying? Not because it starts at 0. It could have been x of n minus 1, plus 1. It could have been any x of n. But x of n is known. It's the input. You're trying to determine the output. You went to the system. You look at its initial conditions. It might be clear there's no initial condition. The system has rested. Or it might be not clear. It has some initial conditions in it. Okay. So therefore, we're going to solve. We're going to find y of n. So the solution, what is the first step? We're going to take the z transform. This is the first step of both sides. What is this z transform going to give me? Y of z minus 5 over 4 z to the -1 multiplied by y of z plus y at -1 multiplied by z to the 1. So y at -1, which is a 4, multiplied by z to the power of 1. Agree? Everybody?
Yeah.
And then plus 1 over 4 z to -2 multiplied by y of z, y of -1, which is a 4, multiplied by z, plus y at -2, which is -4, multiplied by z squared. This comes directly from the expression. So this is y at -1, this is y at -2. Okay, I'm going to write this and then I'm going to come back and explain this. So what is this going to equal to? This is going to equal to x of n. If I take the z transform, it's going to be x of z minus 2 z to -1 x of z plus x of -1 multiplied by z, but this is just 0.
So why is y -1 in that second?
This one?
Yeah. No, yeah, why is that middle term there?
This one?
Yeah.
We'll see in a second. Okay. So what is this term that we calculated here? Is y of n minus 2. Isn't it? This is the z transform of the y of n minus 2. And it looks complicated, but let's see what it really is. So let's say that we have y of n. So I'm going to do it on this side here. I have y of n that has initial conditions. So I have at -1, at -2. This has a value, this has a value. This is y at -2. This is y at -1. Agree? This is what's given. We have y at -2, and we have y at -1. And this is what y looks like. What I want to calculate is what y is going to be when n is 0 or greater. But this is the initial one, the value of y. Now what am I doing here? I'm taking y of n minus 2. Together? What is y of n minus 2? It means I'm shifting y to the right by 2. So if I take this initial conditions and shift them to the right, shift right by 2, what am I going to get? At 0, I'm going to get y of -2, and at 1, I'm going to get y of -1. Agree? Everybody? Y of n minus 2, shift the signal to the right by 2. So I came to the initial condition, shift them to the right by 2. Now if I take the z transform of this signal, what is the z transform of this signal going to equal to? Y at -2 multiplied by z to 0 plus y at -1 multiplied by z to -1. Agree? Everybody? Now if I compare what I got here to what I got here, what did I get here? I got z to -2 multiplied by y of -1 to z, which is going to be y to -1 multiplied by z to -1. And I'm going to get y to -2 multiplied by z to 0, which is y to -2 multiplied by z to 0.
Yeah.
Makes sense? Everybody? So there is no magic about what Lewis is doing here. We're taking the z transform, we're assuming the system is causal. So when it is at -1, -2, we shifted it. So it's going to become, if I take the z transform of these initial conditions, they're going to be placed here. They're going to give me these new terms here. Is that clear? Everybody? So I'm going to just have this multiplied by this is nothing other than this. And this multiplied by this is nothing other than this. So you can use the formula, but this is what the, like even if you forgot the formula, if you did not have that expression for the time shift, you can intuitively produce it by shifting. I shifted the initial conditions and I shifted y of z. Y of z is going to get multiplied by z to -2 because I shifted it to the right by 2. And the initial conditions are going to come in and I'm going to take their values. Is that clear? Everybody? Okay. So continuing, we're going to have y of z multiplied by 1 minus 5 over 4 z to -1 plus 1 over 4 z to -2 This is going to equal to x of z multiplied by 1 minus 2 multiplied by z to -1. And what else I'm going to have? Can you see it? I took y of z, z to -1 multiplied by 5 over 4 y of z, 1 over 4 z to -2 y of z. So this is all taken care. I still have this term, and this term. I'm going to add them together, and I'm going to put them on the right side. So I'm going to have plus 5. And what is the second term going to equal to? Minus z to negative 1. And I'm going to have plus 1. Together? Where is these coming from?
Y path.
They're coming from multiplying this with this, multiplying this with this and this. Is that clear? Everybody? What do these represent again?
M2.
Yeah, but physically, what do they represent? The initial conditions. These are the initial conditions. So I have the output written in terms of the input and the initial conditions. Okay. Again, this is not meant to be confusing, or you could have like done it in 2 steps. You could have multiplied these and factor out x of z, the terms that do not multiply x of z, let's put them on that side. Okay, so therefore, my y of z is going to equal to z squared minus, okay, let me do one more step. So this is, we have all in terms of a negative z. We do not like that. So I'm going to multiply both sides by z squared. So this is going to become z squared minus 5 over 4z plus 1 over 4 equal x of z multiplied by z squared minus 2z plus 6z squared minus z. Which one? The 1 and 5, we add them together. 6. Okay. So therefore, my y of z is going to equal to z squared minus 2z divided by z squared minus 5 over 4z plus 1 over 4 multiplied by x of z plus 6z squared minus z divided by z squared minus 5 over 4z plus 1 over 4. Now when I look at this output, what is this output? There's an output component that is a result of x of z, and there's an output component that is a result of initial conditions, which is what we defined as when we said x equal to 0. So this is output when x is equal to 0. This is the output when initial conditions are equal to 0. Together, they give me the complete output. What is the transfer function of this filter?
It's not clean. You have to do some algebra to get x over there under y, right?
Is that so?
Not sure if you can.
What is the transfer function? The transfer function, by definition,
Is y over x.
y over x when the initial conditions are 0. Together? So if I look at this, if I set the initial conditions are 0, this is going to be gone. Therefore, what is h of z? Z squared minus 2z over z squared minus 5b plus 4.
Yeah.
Make sense? So please keep that in mind. When you have if I have a transfer function and tell you find the output for a given input, what does that mean? It means the initial conditions are assumed 0. Okay. So therefore, we're going to take each one of these components and calculate the inverse z transform for. So we're going to calculate y when initial conditions is equal to 0, which is equal to z squared minus 2z divided by z squared minus 5 over 4z plus 1 over 4 multiplied by x of z. What is x of z equal to? It's a unit step. What is the z transform of unit step?
Z over 1 over Z. Is it plus or minus?
Minus 1.
Yeah, minus 1.
Z over z minus 1.
Minus 1 half.
No, it's a unit step.
But it's a unit
Is the
step.
input? Oh, unit step. Okay, 1/2. Sorry,
It's minus 1/2.
1/2. Good. Z over z minus 1/2, which is the input. Okay. So what do we do? We're going to divide by z. This is going to equal z squared minus 2z divided by z minus 1, z minus 1/4, z minus 1/2, which is going to equal negative 8 over 3 z minus 1 plus negative 7 over 3 divided by z minus 1/4 plus 6 over z minus 1/2. Then we're going to multiply back with the z. So the initial condition 0 is going to be negative 8 over 3 multiplied by z over z minus 1 plus negative 7 over 3 z over z minus 1/4 plus 6z divided by z minus 1/2. What do we do next? Can take the inverse. What is the first term equal to? Anybody?
We're still writing this stuff down.
Negative 8 over 3 dn. Wait, no.
No, there is no.
Yeah, there's-
This is just a multiplication factor. Z over z minus 1 is u of n. And this multiplies it. Okay, the second term, 7 over 3 multiplied by 1 over 4 to the power of n, u of n, plus 6 multiplied by 1/2 to the n, u of n. Where is this output coming from?
Initial conditions.
No,
From the input.
from the input. From the input. And if I look at this output, what's going to happen to these two terms? They're going to die out. This term is 1/2 to the n. When n is very large, it's going to die out. This term is going to die out. So in the steady state, what am I going to have? Negative 8 over 3. Now this is the output that is due to the input. The second component that I have to calculate of the output is the output that is due to initial conditions. So we call this y x equal to 0 of z. Again, when x equal to 0, it means it's the output due to initial conditions. When initial conditions equal, it means the output that is due to x. Okay, so the second component was 6 z squared minus z divided by z squared minus 5 over 4z plus 1 over 4th. Therefore, we're going to take y, x equal to 0 divided by 0, which is going to equal to 6z minus 1 over z minus 1, z minus 1/4, which is going to equal to 20 over 3 z minus 1 plus negative 2 over 3 z minus 1/4. And therefore, y when x is equal to 0 is going to equal to 20 over 3 multiplied by z divided by z minus 1 minus 2 over 3 multiplied by z over z minus 1/4. And y when x is equal y when x is equal to 0 is going to equal to 20 over 3 multiplied by u of n minus 2 over 3 multiplied by 1/4 to the n u of n. Together? So therefore, what is the overall output of the system?
You add them together.
We're going to add them together. Okay, so y of n is going to equal to y that is due to the input plus y that is due to initial conditions. Okay. Is that clear, everybody? So to summarize what we've done, and what everybody should hopefully be very familiar with now, if we have a system, we can represent it by h of n. And this h of n is the output when x of n is equal to delta of n and initial conditions are equal to a 0. The output of the system is h of n. If I take the z transform, this is going to give me h of z. If I take the inverse z transform, it's going to give me back h of n. If I take h of n, if I take h of z, we call this transfer function. If I replace z with e to j omega, I'm going to get h of e to j omega, which is the frequency response. Now if I take h of z and multiply across and inverse by inspection, this is going to give me the difference equation. from 0 to n, 0 to m. Okay, so if I have the difference equation, if I set the initial condition to 0, take the z transform, it's going to give me h of z. If I have h of z, then I can, by inspection, find out what the difference equation is. Does that make sense, everybody? A of z multiplies the y of z. So therefore, these coefficients are going to give me the difference equation terms that multiply y. The numerator multiplies x, so therefore it's going to give me the terms that multiply x. The numerator, denominator. Does that make sense, everybody? We see the relationship between each. If I have x of n in the time domain, and I have it as, I can convolve it with h of n, is going to give me y of n. If I have the values of x of n, I can iterate and calculate the output y of n. If I want to see how in the frequency it's behaving, I can calculate h of z and plot the frequency response of that system. Any questions? Okay, let's stop here. Thank you, everybody.